Charlestown. Okay, cool. Thanks a lot. Well, first of all, thank you for having me here today. It's a pleasure to be talking even more in the first event. And well, my name is Marcelo, as was mentioned. I'm a platform engineer at Airbnb at the moment, but the story that I'm going to talk to you about today is about my previous job at Heycar, another company here in Berlin, very nice company too. And let's go for it. So I worked at Heycar mainly as a site reliability engineer, but I was one of the first backend engineers to be hired as soon after the company was set up. And this is a bit of my background. So practical event-driven architecture, it's a big jargon. Mainly when I was looking for content of practical event-driven, because I was always interested in it, I always found stuff that were very technical and very theoretical, most of this, to the sense of the word. And I was not finding things that were practical. Most of the times they were like examples that are boilerplates, that are examples of things that you can actually apply to your real life, or examples on a perfect world. So this is actually the opposite. The idea is the opposite, is to experience the journey of the team that developed a Heycar from the beginning to the time that I was still there. And all of the reasons that led us to go for an event-driven architecture, and how was to develop it, what were the pieces of it, and what were the parts that worked out well and or not. So to give you a little bit of context about Heycar, so Heycar was a company set up with funding by Volkswagen Financial Services, the bank of Volkswagen. And that implies a little bit that the company had a lot of money and they wanted to scale really fast. So most of the things I'm going to talk about take this context into account. Just to explain a little bit of the company, because it's a bit important. The company is a competitor of Mobility or AutoScout24. And basically we had inventory from car dealerships. We pushed that into our website. We received this through integration. And we show to customers. We acquire customers over traffic on Google, Facebook, and such. The customers go to a website and they generate leads that go back to the dealership. We're going to focus on the first part, but there are two important things here that the company made very clear from day one, was time to market and performance. On the time to market end is that we received this inventory the same time as most of our competitors were receiving at the end. And we had to show this to the customers really quickly, because otherwise our competitors would be the first ones to have the content, and then they would display, and then we would probably miss leads on that end. And second of all, performance. Since there were a lot of TV campaigns planned for the company, and also a lot of budget, a huge budget on advertisement, it was really important that the website would be up all the time. So we had to take those things into account when evaluating. And I'm a traditional person. I had a huge long-term Rails background. And therefore, like, you think I'm just going to put Rails there, and what could go wrong? And what was the setup on that company? So regardless if you're using Rails or not, you know, I'm just talking about a sample architecture and why would not work for us. So you have the car dealerships, you push inventory to an application, this goes to a database, and eventually you have to serve customers traffic. This goes to the database as well, so you already have sort of a queue here where I'm going. Just to be a bit more concise, the CMS that I'm talking about, they were pushing, instead of like delta of inventories every day from the car dealerships, they were pushing a standard in Germany, which is a zip file with CSV and images. It's a very amazing API. So the zip file, the CSV contained the full inventory. So if a car is not there anymore from batch 1, from batch 2, then basically the car was sold or disappeared, I don't know. And the images were always like raw images from the camera, so like 20 megabytes images sometimes, and we had to make sure that was published really fast. If I receive a car batch in the morning, I want to make sure that in a couple of minutes it was on the website. So time to market and performance again, just in case. So what happened when we were trying to publish those things on the platform? You had to make sure to extract all of the information of the car, color, makes and models, and things like that, save on the database. So you get a CSV, you go to the database to make sure that the content is not duplicated already, or if the car exists or not, and you have to make sure. So this is a lot of transactions already in the database. You have to look at all of the financial perspectives, comparing a car with other cars, and the sense of financing, storing data pre-calculated so that you can serve later. You have to look at all makes and models and regulations and emissions and all of that that is required by law. You have to look at all of the images, as I mentioned. Even though you're not storing the images in the database for obvious reasons, you are still sort of acquiring some data or metadata about images so that you can use that in your favor on UX later on. And ranking information also goes to the database, finance information. At the end, we're backed by the bank. So we had to put all of that into the database. And that was really stressing on the database. And on top of all of that, you have to serve traffic from the database, right? So you have all of this business logic that is hard to scale and is also hard to orchestrate, because all of those jobs in theory, they could run in parallel, or maybe some of them depend on each other. So you have this tree of processing that you could follow. And if any of you ever work with Rails, you know, eventually you would be having like a monolith with a Sidekick, and then you would be lost on how to manage all of this because there's no dependency graph on Sidekick and anything like that. So it would be hard to scale, even if most of the monolith architectures would be hard to scale to serve millions of people on this architecture. And at the end, your database becomes the single point of failure because you're using it with two different perspectives. You're using for ingestion and you're using it for traffic serving. So basically, you have your monolith, you write to the database, you read from database, which becomes unreliable when you're trying to do that at scale. It works for thousands of users, maybe 10,000 of users, but does it work for 1 million of users at the same time? And maybe 20 dealerships trying to ingest their payload at the same time? That was what we were getting at. And you might be wondering where events come to play in this thing, because it's almost like 5 minutes and I haven't talked about events yet, and we're getting there. So we tried to look for an experimental approach on top of this in order to make sure that we were doing the best effort on each front. So just imagine traffic flow where you have two different applications or maybe two different ends of an application. And one of them is writing to the database, which is the ingestion. There's a lot of pressure on writing, so I have to scale that end. And what do I need from a database when I'm writing to it and I want to have it as my main source of data? I need it to be consistent. So I needed to make sure that if I write that a car is 5,000 euro and it became 7,000 euro, I have to make sure that every time I read from it is still going to be 7,000 euro. And I need to make sure that it's durable. Maybe 5 years from now, I still want to read this data, and I want to make sure that it's there. And there are obvious perspectives on scaling this database for writes, but we don't have to go this far at this point. And then you have traffic serving, that I have something. It doesn't necessarily has to be a database. It could be something else. We're going to figure that soon. And I need to be performant. As I mentioned, we couldn't be like 3 months ahead in the company, then the engineer, the CEOs hires 100 people for sales. We have 1 million cars on the platform, but then this Sunday afternoon, there's a game on the World Cup, and then we have a TV spot. Then 20,000 people come to the website, and the website doesn't work. So we had to make sure that was one key player, but also the website had to work and had to be fast. So this was one of the things we had to take into account, reliability and performance. And for this part, you need to have isolation between whatever you're reading. It could even be your database, but you have to have some isolation at some extent. And you have to make sure to be able to replicate this. Because if you want to serve this and at scale, things are going to fail. So you must have replicas, backups, and even shards at some extent. And well, that's basically all of the features of a cache, or maybe some of them. And we end up finding out what we wanted from each part of this thing. So we want to read from a cache, but we want to write to a database. And there's where events come to the play, right? Because we have an issue with how do we synchronize this? Most companies that I worked before would use practice or would use ETL jobs or would use batch jobs where you go to the main database, you fetch all of the data you need every half an hour, and then you synchronize to the cache. And that works well if you don't have time to market constraints. So that was one of the deals, because maybe the first time you go there, it works. Half an hour is a time that is good enough for you to copy all of your data to the cache. But maybe the next time I have 2 million cars, and then what now? Does it half an hour work? And if this thing blows up the window that you're trying to replicate, then you're gonna have like, every time someone posts a message or posts a new car on the platform, you have to wait 1 hour for this car to be on the website, and this is not a good experience, not good time to market. So this is where event comes to play, more specifically fan out. So basically, That's what I'm going to be talking about today. How did events and fan out help us to be able to achieve high performance writes on this database in low latency on synchronizing with this cache so that we could achieve everything that we wanted at the beginning. So going again for this architecture, that this is closer to what we had in mind when we started. So we have the car dealerships, the inventory, the ingestion batch, and then we are talking about services. You don't have to be worried about microservices or anything like that. Just bear in mind that this could be a class, or it could be part of your monolith or a component, but in our case, just to be clear, it was individual applications that were running within a cluster. So when you receive this ingestion batch, you're going to be storing it somewhere. Gave you hints that we're using S3 buckets, but you could be storing anywhere. You could be even not storing it, but it would be a bit volatile, because at some point, if the processing fails while you are extracting the zip file or while you're doing something else, it might be an issue for us to be able to retry this. So you're going to be storing it somewhere. And the next thing you have to do is you have to start the processing. So this ingestion service was for us the entry point of receiving files that were the batches and normalizing them into a nomenclature that I can identify later. So the date where it was uploaded and the dealership and the number of the batch for that day. And later on, I have to generate an event, right? So I could myself call the next service in the line and just do this synchronous call. But then you end up having the dual write problem, because what happens here is if I have a service and then the upload to S3 works, and then I'm trying to call the next service, but then it fails. So then I'm like, okay, what do I do now? Do I retry? Or maybe I don't even know that it failed. This is an issue that you're going to face when you have to write to two different applications. Maybe you could do the other way around, and you could rise to the next service saying, I'm going to publish a file on S3, and then you try to publish the file because Amazon is more reliable than you, and then for some reason S3 fails. Then what do you do? So we didn't want to face this sort of issue, so we were trying to delegate as much as possible whenever it was possible. One of the parts what we used S3 is that S3 provides something that you can hook up and connect events. The main file systems provide this thing that you can get callbacks from things that happen within the file system, and then they solve this issue. So basically, every time something gets uploaded to S3, whenever they made sure that it got uploaded to S3, they trigger an event. And we were using those events to publish to an SQSQ, simple queuing service, also something provided by Amazon, not sponsored, just make clear. Basically, most of the things that I'm using from Amazon, that we were using from Amazon, is because it would be really hard to host in the first place, and we didn't have the necessity to host. So this is one of the reasons. But then you think, why am I using a queue here to store this event, not a stream? You might wonder. And well, basically, just to give you a hint, we were using one single consumer for this event. So the queue was something that I had literally to consume as a stateful thing, as not a volatile thing, So basically, every time there was an event, I had to make sure to consume that event, and we didn't want to be spreading this event to multiple services or multiple consumers. So that's why we were using this. And one pretty neat thing is that maybe, let's say, I created a bug on this ingestion service, and for half a day, most of my uploads were working to S3, but the extraction service was failing. I don't know why it was failing. It was just ignoring the files. So we were able to just replay that day. We don't need to ask our dealerships to send the batches again. We could basically just replay events into this queue, and then we could push again to the extraction service. So this was one of the nice features from S3. It's not a native feature, but it's something that it's really easy to be done when you configure it. You have first in, first out, a bit of theory, but not that much. So basically, just make sure that every time I receive a batch, that batch is going to be processed before the next one that I receive. And it's not 100% sure on SQS, but for us, most of the dealerships were sending batches not so close to each other. So if a dealership was sending a batch now, they would only send the next batch in an hour, maybe. They would not send the batch in the next 5 minutes. So it would be fine to have such interval in this sense. And you have the at least once delivery guarantee, meaning that if the upload fails for some, the download on the extraction service or the processing fails, I'm going to be returning the message to the queue. We're going to be talking about this just in a second, but then just make sure that you understand that we are able to retry. So I don't have to write any code for this. The only code I have to write here is this. So this is the consumer. Everything else on that sense was just small chunks of code similar to this, but everything that I have to write will be within that process thing. So I have a loop because I'll always be consuming from that queue. This is the extraction service. And I'll be having an event that I need to pop from the queue, meaning that I will get the event, the time the event was created, the payload, and I would process this event somehow, so all of my business logic goes in there. Then I have to make sure that I myself consider this processing as a success thing or a failed thing. So I can either acknowledge the event and remove it from the queue. So I tell Amazon, hey, I need, this resource was consumed. This is important to understand. And then the event would be acknowledged and no one else, no other processing would process that file again because there's not necessary. And it's a bit dangerous if it would be happening. And the other thing is if it fails, I want to make sure that I return to the queue because then I want someone else to process, some other service to be processing this event. And of course, you can add a lot of metrics for monitoring here because you're going to see through the talk that latency plays a huge factor here. So Amazon knows about this, of course, and they send you a lot of metrics within this event object. And you can do things like calculate the latency that you were processing on each step of the flow. So the S3 bucket, SQS, and extraction service, even though we're talking about a single consumer, I can scale this consumer to multiple instances of it because since they are sharing the queue, but they are consuming it, so they could be reading from the same queue. And if we make sure that the queue is just distributing one message at a time. Amazon has a mechanism on SQS that guarantees that they are not going to be delivering the message to multiple consumers unless you take too long to process. So maybe one extraction service got a zip file of 100 gigabytes, and this happened. And basically, you would time out, and then I would give this process eventually to another consumer because it failed. I don't receive any notification that no one acknowledged it or returned it. After maybe 1 hour, I'm going to push this event, is going to go back to the queue automatically, and it's going to be consumed by another consumer. So what this extraction service was doing as well, every time there were new batches, we were consuming them, extracting, as the name implies, and we were pushing the CSV to a listing service, and this meaning that we wanted to have another thing taking care of deduplicating all of the content, which would eventually go to a database. So this is where it becomes interesting because now I need to, again, I have the same issue that I had before. I need to find out how do I spread this to multiple consumers because once I have this thing as I have inventory changes on a database, those have to be reflected on the cache at some extent. And for that, we had to find out a way to convert these changes on the database to events again. So you might think of several ways of doing it. This thing that we're maybe going to push to, maybe it's easier to identify what it is before we identify how we do it. So it has to be able to be read by multiple consumers, and all of them have to receive the same content over and over. So different than the SQS, where each instance receives the content only once and receives different content, this one has to make sure that all of them receive all of the messages. It's like I'm sending the files to all of them. So multiple consumers, and I have to make sure of the ordering. If I say that a car is blue, and then it become red for some reason, or maybe the price was 5,000 euro and it becomes 7. I want to make sure that this is the order that the events are processed and not the other way around. Otherwise, it will be really weird. So we're talking about a stream. When I say stream, I'm talking either Kinesis stream, either Kafka streams, or NAT stream. You choose your poison in that end. For us at the time, we chose Kinesis from Amazon, not sponsored again, but just to make sure. And we chose that because at the time it was not possible to host, to have a hosted Kafka on Amazon. Now it is possible, so it might be a good thing to play with. But also Kinesis is much easier to start. You don't have to do much. And there's a lot of support from Amazon. You can go pretty far with it. And it's not that hard to switch to Kafka once you understand all of it. So I think it's a nice playground to start with. even though Kafka will be eventually the choice, if you go really at scale, it might be that Kinesis might limit you on that end. And then in the listing service, now I have to publish to that stream. And again, I have the consistency issue. I have to make sure that everything is in the database is in that stream. And I have to do a write problem. Again, I could be writing to the database and then pushing the messages to the stream. Or I could try to maybe write to the stream first and then try to write to the database. And who gets to win is sort of a transaction, and you don't want to be implementing this sort of logic yourself or transactions. So we had to find a way around it. Just to zoom in a little bit onto the listing service, imagine that I receive a post and I'm going to write to the database. We were using Postgres, but most databases, most SQL databases work in similar ways to this. They have different mechanisms, but similar to this. So they have a write-ahead log, which is the way of the database to ensure that they replicate the data across replicas if you're using multiple instances of a database. So that is, whenever I write something to the database, it first will write to the write-ahead log, and then later on, all of the replicas would read this, and only when all of the replicas acknowledge this, then it would make sure to return to me that the data was inserted, because it's fully consistent. That's the idea of the exit paradigm and things like that. So we created something called changes service at the time, and basically connects to the database as a slave replica. And it reads this write-ahead log and finds a way to push this to the listing stream. As an alternative, because most people don't want to be building something like this, we had to do it because of internal reasons that are not really interesting to dive into. But you can use the Debian, which is an open source software that does pretty much the same, and probably much more performant and much more reliable and supported than whatever we created. So just to resume what happens here, let's say I created an insert statement because a new car was on the platform. So I receive a CSV, there's only a new car. I create an insert statement. This insert statement will make sure first that the Debian receives this update and acknowledges it. And then when that happens, it goes to write to database. But the Debian is going to make sure that it's going to write to the listing stream, which is the stream that we post notifications or events about the listing database. So it works pretty neat. At the end, this became the service unit, or whatever you want to call it, but every service was composed of an application, and this application is a RESTful application. It doesn't have to be anything special. The application itself, the code, doesn't even know that I'm doing this change data replication, the change data capture thing on the background. Basically, the database does, so it's infrastructure code. This is a Docker image. You just connect things and then they'll work well. You don't have to write code for it, which is pretty neat. And eventually, all of the events that happens on individual tables of this database will be posted to this stream. We can configure that in each scenario. And those events can be posted as binary events if you want for some performance reason, or maybe even in JSON, or if I want to write in CSV to the stream, I could do that as well, not sure why. And as I mentioned, the listing service is completely unaware. So you could have people that they're doing their daily jobs. I just want to create RESTful services with HTTP. I'm writing the listing service, and I have another team in my company that takes care of this pipeline that is replicating data. They don't have to necessarily communicate, but it would be better if they do, of course. So just recapturing, then this is what happens. On our case, we were using the changes service, and we were pushing JSON payloads to the stream. So every time new event, or a new car is posted, or a new car changed the price for some reason, on that same order, it would be pushed to that stream. This is the unit of the service. Same thing for the pictures. So I'm just replicating here. There's pretty much no code in regards of services besides the logic of the images to be uploaded to S3. But I would be saving image A is from car 1, image B is from car 2, this sort of things I would be saving in the database, and this would get replicated to the image stream as well. So at the end, those streams, they become to be the source for everything that is going to happen next, which is really nice because you don't have to sort of go there, as I mentioned before, and then try to look for the things that changed. You receive them as notifications, as a notification on your phone. There's something else that I can just rely to notify me that something happened. And also, those services, the image batch service and the listing service, they don't know about the next things. So each time I want to push a new consumer, if I want to hook up a new service that needs to receive those events, this new service doesn't have to be registered anywhere. It's there, it's reading, and it starts to read from day one if I have a full-length stream. So imagine that I have the dealership service. This would be a service that would read from the stream, and it would say, okay, this car that just got published, it's from my dealership, or it's from this other dealership, and it would make this connection. So every time a new car is published, a new car changed, I just make sure that I know about this thing. So internally, this service would be not so different from the extraction service. So few lines of code. Of course, I'm not taking into account how I'm processing it, but just the sort of boilerplate around it. Different from the queue, when I'm reading from Kinesis, this is just an example from Kinesis, I have to send the position of the stream because since the items on the queue were consumed, I knew that the next item was the one that was posted next. But for Kinesis, Kinesis doesn't know of where each consumer is reading from those stream. So I can send either the position that I'm reading, maybe the first read, I don't know which position. So I just start from the horizon, which is the first position of the stream. And I have to process the record. They use the word record, not events, because of internal reasons as well. It doesn't have to be important here. But basically, you receive a result from your processing that you stipulate yourself, and you say, okay, I managed to attach this car to a dealership and everything went well, or not. If not, then basically I do nothing because the position just not gonna be updated. Next time I iterate through this loop, I'm gonna be processing the same record. This is also something important from the streaming processing. You have to progress on the stream because we want to ensure ordering. So if I ignore an event, I cannot continue. This is something that is important. And then if you update your position, the next time in the loop, you're going to receive the next record from that position and so on and so forth. Same thing here, you should have metrics for monitoring even more because you have to make sure that the latency is still good. If you're stuck on a single record and not able to continue progressing in the stream. And imagine that, for instance, instead of dealership service that is, let's say, lame, we have the CPU intensive service, something that really to process something that takes a long time. Then you might be wondering, every event on that queue, it's going to take a long time to be processed. I'm going to have a huge latency, but you can also scale the CPU intensive one to run in multiple cores or in parallel, guaranteeing the ordering of the messages, but you just have to make sure which messages I can process in parallel. So if I'm talking about the same car, I should process in sequence because the car was yellow, then the car became blue for some reason, or the car changed the price, I have to process in sequence. But if I'm talking about different cars, I could process them in parallel. I could just say, okay, this car, I can process the message that it was red, and then I can process this other car was blue at the same time. I can receive those cars at the same time. It's not a big issue. And the other interesting thing is that those notifications, as I mentioned before, they scale horizontally, even though I'm displaying vertically. But they scale horizontally because you can add multiple services here. So imagine that you have a service, we call the vehicle service internally, it was a service that was just attaching things like make and model information so that you were really precise on specifying that. Maybe a pricing service where you compare the price against other dealerships or other competitors. In the financing service where you calculate all of the financial possibilities for that car. So I don't have to register those services anywhere. They just declare, I want to read from the stream. I connect to the stream, I read, and they're going to be receiving the events. Maybe I create the dealership service today, and then it's 2 months after that, and then I have 2 months of company running, and then I create the financing service. But I want to make sure that all my cars were with financing calculated. So I just make sure that whenever I create the financing service, I push the cursor of the stream to the beginning, which will make it start from the day one and process all of those cars or events from day one. So all of the cars eventually would have all of the finance information set. And one pretty neat thing here is we also had the image stream, so we could do some fancy stuff with TensorFlow. It was really cool. We created this service that would classify the images, telling us if it was like front of a car, back of a car, interior, exterior. We could also read from the image stream because there were new images being published and classify them. And at the end, you have a lot of distributed data and distributed services, and they are all spread around. And then it goes back to the question, so I have all of these databases with fragments of my data, whereas before I had the data in a single place, was really easy to fetch, really easy to find. And I still have to have a front-end application somewhere, which is going to read from all of these databases somehow, and is going to publish to the customers, right? So the customer opens the website, what do I do now? Where do I pull data from? So when you look at this, a lot of people just think GraphQL, because I have a lot of databases. I just implement GraphQL in all my services and everything was going to go well. But again, you go back to the beginning where those databases, they are set to be consistent and they're set to be very performant on writes. They're not set to be read gazillion of times. So if I have 1 million people trying to do this, it's going to break at some point. And it's going to have a lot of operational overload on the front ends to be requesting all of that before I serve the consumer. So instead, we decided to continue with the same approach, because now we have to also make sure that all of those things become events. So we connect the same way we connected to the listing stream. We connect all of those databases to the replication slot, and then we push those two streams. Then instead of having databases now with the data, I have streams with the data. And all of those streams, they are also fragmented. So I still haven't solved the fragmentation issue. I need to do something with them that I can sort of merge them, right? I need to merge all of those events and have everything in a single place. Then we created this thing called aggregation service, which basically does that. So how does it do that? Because it's a bit tricky. I receive events that are duplications of the same car multiple times with different features. So the listing stream was the main entry point for this, and then you would have an ID. So this is the identifiers, UID standard. And then this is the way everything else is connected to it, because an image belongs to a listing. Listing is just a part of a car. I forgot to mention that in the beginning. But basically, an image is connected to a listing, financing has to be connected to a listing, pricing has to be connected to a listing, a vehicle. So all of that would become part of a big table that we would have somewhere in this aggregation service. That was the theory behind it. So I have columns. Each column is just a JSON of the last update that I received of this document. So imagine that I have car 1, and then it goes to the first row, and then I have a dealership that says, okay, this car is mine. Then it goes to the dealership column as an update. And then some financing system says, okay, I have this financing for this car. It goes to a different column here. So I have all of the data of the car in a single place. So it's sort of a document or an aggregation or a hydrated document where I got a single listing, which was my root, my source. And then I started to wait for all of the events from those things to get there. So here is nice because I can also define the logic of what needs to be ready, that thing that we talked about in the beginning, which things I have to process in parallel or in serial. This thing ensures that I need, for instance, I need listing to be publishing on a website, but I don't need maybe financing. I can publish just with the price of the car. In the beginning, if the financing comes, I will update my cache. So that's good enough. So this became a service on itself that was really from all of those streams and sort of merging all of the events into a single database. But instead of processing them, it was just getting the payload from other systems that process them. And this thing has a database, so I can do the same thing over and over. I can, again, connect to a change data capture system, and I can push it to a stream, which this stream now, instead of being a stream of events of a specific service, is an event aggregated stream, which gives me the last version of everything I need from that listing so I can push it into the website. So I just put it into Elasticsearch because then I have a search engine, which instead of having like just the idea of the car or maybe part of the features, it has the full document. And that plays really well with the front end because I can just write something that simulates some queries and have something preset there. And then it's going to be reading from Elasticsearch, and this Elasticsearch is going to give me also the ability to search for stuff. It's going to be able to replicate, but it doesn't end there. That's the fun part. It's a stream. Elasticsearch is one of the consumers on that end, but I could do more with this. One of the things that it was not necessarily planned, but it became part of the core features of the company is that all of the data warehousing was free. Like I didn't have to write any ATL jobs to go fetch the data in all of those databases. I just had to read from this aggregation stream, And even better than ATL jobs, I had the changes. I had this dealership is switching the price of the car every day. I had that for free. I didn't have to implement anything other than what I already did. So I could do a lot of data analysis on top of this in Figure, for instance. This dealership is trying to lower the price of cars near Black Friday, but they actually increased the price 2 weeks ago. This sort of thing we could figure because we had all of the history of the car as part of the architecture. And you could hook up anything to that stream, and then maybe you want a dashboard that every time a red Porsche appears on the stream, I want to ring a bell somewhere, or I want to have something that is hooked up to an analytics tool or a dashboard, and I can do that really easily. You just read from the stream and ignore every other event. And one thing that played really well for us is that we could also read marketing feeds from this stream. We were integrating with Google, with Facebook, and a lot of strategical integrations where we had to push all of our inventory there, but it had to be our data. It couldn't be data from the CMS that we received from other parts. It had to be our data shaped in our way with our pictures, this sort of thing. And this aggregation stream plays really well because I could just, instead of pushing my inventory every morning to Facebook and then they would have sort of stale inventory, it's the same issue. I would just push Delta updates to Facebook and then they will just update this car, change the price, but not the full inventory. And that was instantaneous at some point. So let's look, I talked a lot, so let's look at an overview of the entire thing and try to look chunk by chunk so that we understand a bit more how it was working. So the first thing I sort of classified as an ingestion. The second thing is fan out, and the third part is traffic serving, because we have to go back to the workflows of isolation. But it's really hard to define where ingestion ends and where fan out begins. I try to put it the best way I can. So you have the inventory gets pushed, you have the queue, you have the listing stream, which is sort of a core stream, is where all of the events start. And then you have this stream of workers. So the nice part here is that once I'm past the aggregation service, I'm on my cache, it's sort of like I don't care about anything in the first place. I don't care about anything before that. Because if the aggregation service goes on fire, because a lot of dealerships started to push events, I can still scale my traffic. I don't receive more events on that aggregation stream. Nothing happens. I don't have more rights, but I can still read as much as I want. If I want to serve 10 million users here, I just make sure that I scale my reads on the cache, right? So I have a cluster that already is fed with the data. Of course, I'm going to stop receiving updates, but my traffic is not going to be affected by that. It's just that I'm going to get stale content. And the nice part here as well is that if at some point I want to do a big migration or anything like that, I have this possibility of pushing to, maybe I'm going to change the schema. I just push to a new index on Elasticsearch and I'm okay with it. I just release after all of the data has been replayed. So I could replay events from all of those. Those are some of the places where I could replay data from, but not all. And the nice part is that, for instance, as I mentioned before, if you have a financing thing that needs, maybe I generated version 2 of my financing. Now it's calculating with Volkswagen Bank, but also with Porsche Bank. Then I could basically just create a new financing model and then set the cursor of that consumer to the beginning of the stream. It would calculate all of the cars on that bank without I having to do much. So it's really cool. And you can connect multiple, you can connect multiple services to this thing, maybe new services, and they would all receive historical data. One thing that you have to look for is latency here. So we were measuring latency from the queue to all the cache. So basically, how long does it take for the data to go through all of those systems? Because I mean, I'm talking half an hour, so there's a lot of, there's a long path for the data to go through. And in our scenario, I cannot probably share a lot of information on how long it would take, but I would say it's less than 10 seconds. I can promise you that. The data was not taking less than, much more than that to be processed on the worst case scenario. Best case scenario, you would be under a second for sure. So you have to measure this because it could be that one service is not publishing its data, but the document is arriving there. So there's a lot of other sides to this. And as I mentioned, those components are scalable. If I want to have 1 million services reading from the same stream, I would be able to. I just have to probably call Amazon and tell them that I'm going to have a lot of reads. The good part is that those services, they end up having not a lot of responsibility. Internally, a service doesn't know which sort of role it plays on the infrastructure. It just knows which role it has to do of, like, I receive an event, I process it, I save it on this database, that's my job. So this thing made me learn, at least personally, that infra is much better than code in that sense. I don't have to maintain much of the infra. At some point I could just replace it because it's so small in code-wise that there's not a lot of things to be tested or a lot of things to be specified within the code that I write. The tools that I'm using, they probably have been tested and I can just ensure that they work for my use case, but I don't have to QA all of the tools. I don't have to do anything like that. I can replace and I can replicate infrastructure much easier than I can do with code. So this was a learning for me. And eventually you could have bottlenecks on your system. Maybe you have a long time for a specific thing to be happening on the aggregation service, and then it's taking your whole pipeline to increase its latency. So one thing you can do is you can start to use sharding, which is the thing that we just talked briefly before. It's not as easy sort of we could dive into, but basically you just parallelize events that can be parallelized. So you can parallelize events among documents. This is something pretty nice, but you can also parallelize events among dealerships. You can say, any events from this dealership I have to consume in series, but anything else I can consume in parallel. So this is a lot of different things you can do to improve the bottlenecks, but it took us a long time to even consider sharding. And at least before I leave the company, we hadn't implemented anything like that because most of the events were easy to be read from the streaming series. So then I have here a bit of the topics that caught my interest and then helped me to understand what I had to do in regards of code. So maybe, probably we'll find a way to share the presentation later and you can read this for yourselves. But just some highlights, so change data capture, data replication, and how the database does that because we delegate this job to the database. Queue versus stream, which kind of guarantees I want, maybe I want at least once, at most once. It depends on each infrastructure, how you're gonna be setting this up. Single versus multiple consumers, sharding. Eventual consistency is just the understanding the concept that sometimes maybe someone is gonna call you and say, hey, I just saw on the internal tool that the car is red. Why is it still blue on the website? And then they refresh the page and it's blue. And then, you know, understanding this concept and make sure that the culture of the company is based on that things are not going to be instantaneous as they are when you have a single database is something really important. We had numerous support tickets or things like that where you would just say, hey, can you try to refresh the page in like 10 seconds and it would just work. Because people were still used to other systems in other companies where the dashboard is your main source of truth. If the dashboard says the car is blue, the car is going to be blue on the website. Whereas for us, there's a pipeline. We had to make sure everyone inside of the company would understand that. It's something that I didn't think of before actually doing it. So it was a nice learning as well. And it's a trade-off because you're going to have to give up on something if you know a little bit about the CAP theorem. You're going to have to give up on something if you want to have more performance. So it's the way to sell it to the CTO. So, or maybe to the CEO, depending on your company. So latency, so I talked a little bit about that. There's this really nice thing that I put it here as a special topic, shouldn't be, but just in case. There's this tool called Bentos. I'm not sure if you all like Shell as much as I do, but basically in Shell, everything is a pipe, which is basically a stream, and you can hook up a lot of things in parallel and process them. But at some point, you can also manipulate the values of the events. Maybe you want to filter events. So this thing is basically that for any stream source of data. It could be Kinesis, it could be Kafka or anything like that. You can read from streams, you can filter events, or you can maybe select a special event and add more information to it or remove payloads from it. Maybe you can do this, for instance, to be GDPR compliant. Every time I see an email on a stream, I remove from the stream, you know. And this thing is really cool because it helps you to sort of play and hook up all of these pipes. At the end, we become plumbers rather than developers. So this thing helps a lot. And one thing that I've never took too seriously until I had to was to work with very well-defined schemas for those streams, because most of those things will be JSON. At some point, people are going to be complaining about where's my field, this value is an array, should be an object, this sort of things. So having a good and well-spread, well-defined schema for your streams and for your events helps a lot in the long run. So you can look for things like Thrift and protobufs. They're really, really good. And also they're more performant as well. The tooling is going to be a bit worse in some cases, because if you open an event on a JSON stream, you know what to look for. If you open a binary stream, you're not a computer. So you're going to have you give up some of the practical parts of JSON, but you can enhance your performance a lot by doing that. I think that's it. So I will say thank you for listening to me for half an hour about this interesting topic, and open to questions, I guess.
I want to say most of the things I saw tonight were pretty impressive. Marcelo, thank you very much for your talk. Audience, please give a warm welcome to our guest. Muito obrigado again.
Thank you.
Famous last words. We're trying to repeat this. Please provide feedback, talk to the people, mingle a little bit. There's beer, there's pizza, and please attend to the follow-up events. Thanks. Have a good night.